This is Chemistry Unit 7, Stoichiometry. When you know the amount of a substance in a reaction, you can calculate the amount of any substance created or used in the reaction. And in chemistry, these amounts are usually expressed in units of moles or grams. The method used to calculate these quantities involved in a chemical reaction is called stoichiometry. And just to break that word down, stoichion means number and metron means measure. Now there are several types of stoichiometric reactions, and we will learn these by types. So the first type is called mole to mole. So let's look at example 1a here to help you understand this. It says if 0.25 moles of nitrogen gas, which is right here, it's the N2, reacts with oxygen gas, O2, how many moles of dinitrogen trioxide, which is the N2O3, will be produced? So you have been provided the balanced chemical equation. It is your job to figure out the amounts being asked of you. If you're given so much of one substance, how much of the other can be produced? And in this instance, it'll all be moles. That's why it's called mole to mole. So the point here is, we're talking about nitrogen gas at the beginning, and we're being asked to figure out dinitrogen trioxide. So if you were using just the balanced equation, 2 moles of nitrogen would yield 2 moles of dinitrogen trioxide. But we're changing this now. Instead of 2 moles of nitrogen, what if I had 0.25 moles of nitrogen? How much N2O3 would be produced? So we'll set this up using dimensional analysis. So you start with the 0.25 moles of nitrogen. That's my starting point. Now you can see here's the t-square, and I've set up what's called the mole-to-mole ratio. I've just written mole on the top and mole on the bottom. Now I'm starting with N2, so that's why N2 is on the bottom. I'm trying to cancel that, and I'm looking to figure out how much of N2O3 is being produced. So that's the substance that goes on the top. Now where did the 2's come from? The 2's are the coefficients. So if you look in front of each formula, N2 has a 2 in front, so that's why there's a 2 here, and N2O3 has a 2 in front. Now you may have already been able to see this, that if 2 moles of nitrogen produce 2 moles of dinitrogen trioxide, 0.25 moles would also yield 0.25 moles. They have the same coefficient. But that's not always going to be the case, so I wanted to make sure you understood this setup and understood what you are doing before it gets more complicated. So you don't have to put this one in the calculator if you see that the 2's cancel, but you can plug it in if you want to. It would be 0.25 times 2 divided by 2, and it would yield the same amount. So this is not always the case, but this is a good starting point to help you see how to set up a mole-to-mole ratio. Okay. So let's try another one. Example 1b, how many moles of oxygen gas will be produced by decomposing 5.8 moles of water? So here is our decomposition of water. We have 2 moles of water, yields 2 moles of hydrogen and 1 mole of oxygen. But we're not starting with 2 moles of water, we are starting with 5.8 moles of water. So if we change this now, this is now 5.8, how much oxygen will be produced? So here's how you set this up. You start the 5.8 moles of water, which is the starting point. You draw your t-square, put in your mole-to-mole ratio. And now in terms of the substances, you want H2 on the bottom, because that's what you started with, and you're trying to determine oxygen. So O2 goes on the top. And now you look for their coefficients. So in front of oxygen, there is no coefficient. That doesn't mean 0. That actually assumes 1. So this is 1 mole of oxygen. And then in front of water, you have a 2. So that's why there's a 2 on the bottom. Now to solve this in your calculator, it's 5.8 times 1 divided by 2. And my answer is 2.9 moles of oxygen. And now you should start paying attention to your significant figures. I want 2 in my answer because there were 2 in the value that I started with. And then make sure you do indicate your units, its mole, and also the substance that you are trying to find. So it's 2.9 moles of oxygen. And one more. Example 1C, calculate the number of moles of oxygen needed to react exactly with 4.3 moles of propane in a combustion reaction. So here we have propane, there's 1 mole of it, plus 5 moles of oxygen yields 3 moles of carbon dioxide and 4 moles of water. But in the problem, we don't have 1 mole of propane, you have 4.3 moles of propane. So now the question is, if you have 4.3 moles of propane, how much oxygen do you now need for this combustion reaction? So the setup is the same. You start with 4.30 moles of propane, which is C3H8. Set up your T-square and your mole-to-mole ratio. Now you want C3H8 on the bottom because you're trying to cancel that, and you put the O2 on the top because that's what we're being asked to determine. And now where do these numbers come from? You have to look at C3H8. There's no coefficients. That indicates 1. And in front of the oxygen, you have 5. And now to solve, 4.30 times 5 divided by 1. So the answer is 21.5 moles of oxygen. So these are mole-to-mole ratios.